Oh, yeah, go ahead.
This is going to be on the final, these sections?
These sections will hypothetically, yes. Like I can't say for certain. I still haven't been able to look at the exam yet, the final, but it will be cumulative. My hope is that it will just be a 4.1 or a 4.2 system. 4.3, as I was saying, 4.3 might show up, but 4.3, the frustrating thing about that is that 4.3, you won't see it again until 283, which is when you're talking about solving things of the form. Instead of a single variable function, you'll have functions of two variables. Something like this. And the question is, where does what calculus is all about? It stems on two things. It's trying to find the maximums and minimums of a curve just by giving its function without knowing what it looks like, and finding tangent lines or tangent planes to those curves. Or it's about finding the area under something, the area under or the volume under a curve or under a surface or whatever. And so you'll have to find the partial derivatives and set them equal to each other. So you're going to be solving nonlinear systems in that course. But that, like, by the time you're in Math 283, no, that's not uniform. No, like 4.3, like we're gonna be seeing the effects of it, but not actually utilizing it, like not utilizing it in the calculus way. So like the frustrating thing to me is that by the time you get to that point, you would have the mathematical maturity to understand what's going on. So it wouldn't like you would be able to see it and immediately pick it up. So I don't understand why we talk about it in this course. It's a cool concept, but it's just not as useful as one might think. Okay, there you go. So, all right. Yes, JT. Oh, JT and JT. Yes.
When you get the exam, are you going to be making a practice exam?
For the final?
Yeah.
No. So I'd like you to go over the old exam reviews for those things. Those should be sufficient. Along with for unit 4, I don't know if I'm going to have time to make something for it. But the examples that we go over should be sufficient. And then also like any of the questions, like there's not going to be any like nuanced questions because this is the very, very end. They're not looking for any niche questions in this material. It's going to be probably just standard stuff. It's not going to be like remember that one problem on the exam 3 review? It was like, here's the lines of b to the x, a to the x, c to the x, and d to the x, where it's very conceptual. That stuff is not going to be what we're concerned about here. So like any question on any topic on Alex, that would be a good option for practice.
So like on the reviews where it's like question 1 and there's like A, B, C, D, like all the different examples, like the first couple are more like will be on the final. They're always like a lot easier.
The goal, so like once again, I don't make the exam, so I can't say for certain. The goal is for them to be overarching themes. So it should be an overarching theme of the course.
180, what's that math you were talking about?
283.
283, and what is that for?
That is Calc 3. That's for like pretty much you only really need Calc 3 if you're going into STEM. Specifically like physics-based STEM. So if you need to take a lot of physics, if you need to go really high into it, like an engineer, you'll have to take Calc 3. It's high. Engineering, you probably like depending on the engineering, there might be a few situations where you don't need to take it. But there's a lot of very, very useful things in Calc 3. For example, studying like, so what you'll see in Calc 3 is you'll see a surface like this. Yes. I know it looks like a jelly bean. Well, not like one of those trolley worms or whatever. It's one of those terrible gummy beans, jelly beans, gummy worms, whatever. And you want to know specifically right here, you can draw a tangent plane right there. And then what ends up happening is you have a vector going up and a vector going parallel to the plane. And you can do that on any part of the surface. You can calculate what we call a tangent plane for any point on the surface. And one of the things that you study is how these things affect the different surface on different levels. And There's even more other things. There's a thing called a tensor, which later on, but it's kind of describing multiple variables of things on a surface and how things different things interact with it. There's like the one that I was just looking at was a tensor that was talking about surface pressure on a shape. So like if you push it right here, or like if you push the surface right here, what happens at the over here and here? How does it move and stuff? So they're like that's a lot about fluid dynamics and things like that. There's a lot to be said about 283. It does have a lot of useful applications, but those will be something later on. And people always get worried when they see calculus and stuff like that. What I will tell you is once you get there, it's like you always like, I don't know if you were like me, whenever I started a new course, a new school year, I always thought like I was gonna have an exam on the first day. And like I had to know everything about the course when I got there, but that's not the case. Calculus will slowly demystify itself. So, okay. Any other questions? Alrighty. So this might be something that is something you've already seen before, and if so, that's great. If not, we're all coming from different backgrounds, and that's fine. That's what we're here for. So systems of equations. So a solution, or sorry, not a solution, a system of equations is a collection of two or more equations involving two or more variables. We say this system is linear if all the equations are raised, all the variables in the equations are raised to the first power. Otherwise, it's nonlinear. And I suppose I should say, like, if all variables are only being are not being applied to anything, they're just to the first power. And so, this is something that you will hear a lot of mathematicians say, even though we like, so it's a system of equations. You could look at this and say this is a system of two equations and two unknowns, or you could say two variables and two equations. However you want to say it is fine. However, you will always hear mathematicians, especially as you move on further, call them n by n or n by m systems. And what it is this is the number of equations, and this is the number of variables. Always number of equations, i.e. the number of rows, versus the number of variables, which will be your columns. It's all like, now, is this super important for us in this course? No, but I want us to start getting used to this notation so that we don't get blindsided by it in the future. If you plan on taking linear algebra, which if you are going to take anything in engineering, you'll probably need to study linear algebra. If you need to use linear algebra, by the way, if you are doing anything with a higher math degree, please spend as much time as you can learning linear algebra. It shows up everywhere. It's surprising. I wish I had known that going into being a math major, and that I didn't have to go back and relearn it before everything else. It saves a lot. Either way, it's always rows then columns. So equations then variables. So this is a 2x2 system because it has two equations and two unknowns, two variables. And it's a linear system because all the variables are raised to the first power. There's no function being applied to them like an e or whatever. And the next one has three equations and two variables. So it's a 3x2 system. And it's nonlinear because of the things like the x squared and the natural log of y. That's what makes it nonlinear. Sure, the first equation is a linear equation, but the other two are not. And last but not least, we've got a 3x3 linear system. There are three equations, three variables, and all of them are being raised to the first power. And so it is a 3x3 linear system. Yes.
How do you make it
three equations or three variables? So great question, because we're going to see this. Technically, this is plus 0y. So like the second equation, even though it involves two variables, in the context of the larger scene, if you will, there is three variables because at least one of the equations in the system has three variables. Okay. That's a good point because this right here x plus y plus z equals 1, and then x equals 2, and x plus z equals 5. This is still a 2 by this is a 3 by 3 system. Because, yes, because the other ones are zeros. One of the equations involves 3 variables, and the curly brace is suggesting that this is a collection of these 3 systems, or these three equations. So we have to choose like the most amount of variables that are present and the most amount of equations. Yes.
Oh, okay, that's what I was saying. If there was like 2 of the equations only showed like an x and a number, you would still count it as a 3 variable equation if one of them has 3.
Yes. All right. So in this section, we're going to primarily focus on 2 by 2 systems, and a solution to a 2 by 2 system. A solution to a 2 variable system. It could be a 2 by 2, it could be a 3 by 2, it could be a 5 by 2, whatever it may be. But if you have a 2 variable system, is an ordered pair x comma y that satisfies all the equations in the system. So it solves all of them. Similarly, for a 3 variable system, where it's an ordered triple, or a 4 variable system would be an ordered quadruple, and so on and so forth. So we're going to determine whether 7, 1 and 4, 2 are solutions to the system below. What it means is we're going to take, let's work with the first point. So I'm going to color code it 7, -1. Is this a solution? So we'll plug in 7 for x. So what this means is that x will equal 7 and y will equal -1. And if it's a solution to the system, it will be a solution to both equations. So we'll first plug it into the first equation. So does 7 plus -1, does that equal 6? And does 6 equal 6? Yes, it does. So it solves the first equation. But that's not enough. Just because it solves one of the equations, it doesn't mean it solves the other. So we'll check the second equation. So first EQ, second EQ. Does 2 times 7 minus 5 times -1, does that equal -2? And so 2 times 7 will be 14. And then plus 5, does 19 equal 2? Well, no, it doesn't. Of course not. Unless we're dealing with Z mod 2Z, then if we're working in modular arithmetic, then maybe, but that's not the case. So this is not a solution. To the system. So that's no good. But then we'll check 4, 2. And so this time I'm not going to color code. It was just to see it in action, how we're doing it. We're plugging in the x into the x coordinates, the y into the y coordinates, and calling it good. But then 4, 2, that means x is equal to 4 and y is equal to 2. So does 4 plus 2, does that equal 6? Yes, it does. And then does 2 times 4 minus 5 times 2, does that equal -2? And yes, it does. You get 8 minus 10, that's 2. No, sorry, -2. So it works. So 4, 2 was a solution. So 4, 2 was a solution. 7, -1 was not. Now, we're going to be doing the old-fashioned way, but later on in mathematics, you'll find faster ways to do this. And then in addition, I mean, for the most part, we usually have computers doing this now, but it's important to know how the computers solve it. And they solve it with a process called Gaussian elimination, but you'll get to that later on. We're going to start with the first ones. And I want to focus on the geometric implications and trying to figure out why these things are solvable. This is actually one of the most useful applications in mathematics. There's an entire field called linear optimization, and then its sister course called nonlinear optimization. But those are very, very useful things that have real life implications. Trying to figure out how to optimize, like the one I always bring up is imagine you're a cleaning company and you're trying to make a bunch of different detergents. They all already have the same type of chemical with a couple things thrown into the mix. You're trying to maximize your profits when you consider how much you have to travel, how much you have to purchase of your detergent from a company, or your chemical compounds from a different company, and you're trying to maximize profits while minimizing costs. You use matrices, you use systems of equations to figure that out. So now the observation is that in a 2x2 system, in a 2x2 linear system, each equation could be remanipulated to be in the format of y equals mx plus b, right? For this one, we'd have just to subtract x. Here, we'd have to subtract 2x and then divide by -5. But either way, we could get them into the format of y equals mx plus b, or a line. So the point is as such, these systems represent two lines, and the solutions to the systems are where they intersect. These systems represent two lines to the and the solutions to the system, which is an ordered tuple, it's an ordered pair. That's going to be where they intersect. Because remember, a solution to to an equation, just a one equation, is a point on that curve, right? If we talk about the curve x squared plus y squared equals 1, that's a circle, right? And if I plug in the point 0, 1, it's a point on the curve, because 0 squared plus 1 squared does equal 1. So any point that solves the equation is like any point that solve let me restate, any ordered pair that can be plugged into the equation and make a true statement, that ends up being a point on the curve. And so what we're trying to look for is a point that's on both curves, i.e. a point where they intersect. And so we get a very, very fascinating situation when it comes to linear equations. But every equation can fit into this definition. Now, if these definitions ever become needed, I will provide the definition for you on the final exam. This is something that usually is just meant to be done with Math 253, which is linear algebra, but I want us to know the terminology because it might show up on the homework in terms of that. So just keep this page open on your homework just so you can see how it's done. But for the most part, we're only going to be really working with one solution situations. A system is said to be inconsistent if the system has no solution. How can a system have no solution? We'll see in just a moment. But inconsistent kind of makes sense, right? If it's inconsistent, it means that it doesn't make sense. It's inconsistent, meaning it should have no solution. And then if it has at least one solution, we call it a consistent system. Now, here's where the weird stuff, like the weird definitions happen. And it's annoying because I always find myself, when I was taking this course, I always found myself getting these two terminologies mixed up. I wish there was better terminology, but there isn't. At least mathematicians haven't decided to change it. When a system has exactly one solution, we say that it is an independent system. And if there are infinitely many solutions, we say that it is a dependent system. And the way I've tried to visualize it in my head is, if the reason why exactly one solution means that it's independent is there was always going to be one solution. There was never any other doubt. It independent of what the equation really was, where the point was going to be. Whereas we say it's dependent, it depends upon the equations. The two equations that are present, they must be dependent upon each other, and you'll see in just a second. Once again, I'm not going to test you on that terminology. Alex might bring it up in one or two situations, but I don't think that it's actually going to ask you to choose those terminologies. And if it does, just have this page in front of you. That's the only thing that's going to be necessary. All the exams stuff, it's probably going to be consistent, independent systems. So it's going to be just trying to solve a system. So how do we get these different situations? If the lines are parallel, what we learned in geometry is that parallel lines never intersect unless we're talking about hyperbolic geometry, or sorry, not hyperbolic, elliptical geometry, in which case we wouldn't be taking, like, that would be an upper division math course. So in our field of study, parallel lines will never intersect. So the number of solutions is none. In terms of the definition terminology, this is an inconsistent system. It has no solution, hence is inconsistent. And so the solution type is NA. Now, the algebra giveaway, I'll get to it in just a moment. You could have the lines intersect. Nice and neat. These two lines are skewed, but they could be perpendicular. As long as they cross through each other, then there's one solution. And so this is a consistent and independent system. And the solution point is an ordered pair. Going to be, in this case, it's 2, -1. Now, I want us to gush about this next one for a second. This one took me a long time to do, and I want us to appreciate it. Drawing that equation, like creating that line, because that's not two lines stacked on top of each other. I had to really, really work to figure out how to make it so that it was half red and half blue. I tried many different formulations until finally I figured out what to do, and I did it. And I even did it to the equation. Do you see how cool that is? It's got a little red up there, a little blue down there. Spent way too long on that. I was up until 1 a.m. trying to figure it out one time. And so I just want us to have an ooh or an ah in the back of our heads, just saying how cool that is. Thank you. That'll keep me going for another day or two. So if both equations end up representing the same line, so it says that like the double color is trying to suggest that, but perhaps one of the equations is saying, let's see here, negative x plus 2y equals 2. And you could also have negative 4x, or sorry, positive 4x minus 8y equals -8. Those are the exact same equation, just written differently. I guarantee you, if you try and solve for y in either one of them, you'll get back to y equals 1/2 x. So this could be your system, and it's just the same equation both times. That can happen, in which case, every single point, is a point of intersection. Because every point is a point on the curve. Every point is a solution because it solves both the equations, because both equations are the same line. And so in this case, we have infinitely many. And so this is a consistent system. It's consistent because it does have a solution, but it's dependent because it depended on the equations that were given in the system. And this is the most annoying one in terms of how to write the solution. In this course, honestly, I'm going to bypass it and say, as long as you say that there are infinitely many solutions, I'll give you full credit. Later on, once you get to 253, then you want to write what the like the solution set of this equation would be, because it's not just one value anymore. It's infinitely many. So how do we represent infinitely many? So the verbal way to say it is it's all points on the line y equals 1/2 x plus 1, or yeah, x plus 1. Or the way that many textbooks will want you to write it, it's all the points x comma 1/2 x plus 1. This is our y value. And I'll explain why in just a moment. Since you've written it down. So it's all the points on the line that they both ended up equaling. But if you want to write that mathematically, now, like if I wanted to be really, really, really mathy about it, I would write this. So you don't write this, but I would write x such that we have the point x comma 1/2 x plus 1. It would be the collection of all the, like, so the way that's read in mathematics, that's the curly braces mean the set. And then, so it's the set of all x, and the vertical line means such that. So it says the set of all x such that it's the point x comma 1/2 x plus 1. That's the mathy definition, but we don't need to worry about that really. The main thing is understanding that it's all the points on the curve. So this might look weird at first, but this makes sense. This point right here for an arbitrary x, let's say instead, maybe not for an arbitrary x, let's call this a right here. Don't know what that value is, somewhere between -3 and -4, but we don't know. How would I describe this point? I'd plug it into the equation to find the y value, right? The x value I chose, and then the y value will come from plugging in the x value. So I'd plug it into this equation. I'd get, so y of a would be 1/2 a plus 1. So this point has an x value of a and a y value of 1/2 a plus 1. And so that was one random point. I can easily bring this all around. I could, like, that was just a generic option. I could bring that over here, right there. And that's a point a comma 1/2 a plus 1. It's all those points. That's what's going on. That's the, like, so, but instead of writing it as a, you write it as x because it's dependent upon x. I guess that's the best description of it. So if it asks you to write the solutions to a consistent dependent system, an infinite system, you write it like that. You write x comma the line. In general, so we can even write this on this down below, or yeah. In general, it's x comma mx plus b, where this is your line. This is the line. The equations become, the EQs become. And JT, I think you had a question.
Yes, are you saying that that's y, or is that y over?
Oh, sorry, that should be a curly brace. So let me make that a little bit more clear. So this is y. Now it's looking like a weird lily. That's why. Does that make sense? Yeah. That's your y value. Oh, and the 1/2 got deleted. The 1. Okay. Now, so once again, I'm doing this just so that you see how to do it. Please keep this page open during your notes so that if it does, I think I removed all of them, but if I didn't, just keep this page open. I don't need you to know the terminology. What I do need you to know is whether or not it has a solution, doesn't have a solution, or has infinitely many. And that's where we're going to talk about here, the algebra giveaway. The algebra giveaway. Because we're going to learn how to solve these things algebraically. Now, you'll have an inconsistent system if when solving, you get a false statement. Like 0 equals 2 or -5 equals +7. Anything like that. If you get a false statement when you're solving it, that means that there is no solution. When solving, if you get a false statement, there's no solution. It's an inconsistent system, but all you need to say to me is no solution. And the reason why that's the case, I hope this makes sense. The reason why this means that there's no solution is that when you did all the valid algebra that's at your disposal, right? Adding and subtracting things from both sides, substitution, whatever it may be, when you did all the valid mathematical stuff, you still ended up with an untrue statement. So it didn't matter what X and Y were. At the end of the day, it was never going to work because no matter what algebra we did, we always got to a false statement. And that's how you know that you have an inconsistent system, a no solution system. The algebra gave away that you're in a consistent independent. So one solution is that you, in fact, when solving, you get exactly one X/Y value, i.e. a unique solution. If you plan on taking a lot of math in your later years, you will hear that terminology of a unique thing a lot. Mathematicians, we love talking about unique solutions. I don't know why, but we just do. That's a terrible E. It's i.e. a unique solution. And I don't even remember what IE stands for. I think does anybody know? It's Latin. I don't remember. I think it's like
trivia night with a couple beers, man, that would thing pop up there.
Oh man, that's like that's probably that's a crossword clue. That's a crossword clue right there.
Yeah.
I like to make up my own definition, but an example.
I think that's actually what it's supposed to mean. It's just the Latin statement for in an example. Yeah.
Did Alex just ask the number of solutions?
I think so. I think that's what it's going to do. So you don't need to necessarily really worry about the terminology, but like if you look at an explanation on Alex, it will say that there are things consistent, independent, consistent.
Similar to what we did on one of our last policies. I feel like I did this on Alex.
You might have, like in some ways we were doing it when we talked about lines because these are closely related to lines.
Okay.
So this is the natural extension of one line to talk about two lines or three lines and so on and so forth. And then the last one. So when solving, you either get a false statement or you get exactly one X value. How do you think you know you have a consistent dependent system, an infinite many? You get a true, you equal each other. You get a true statement. So when solving, you get a true statement. Like 5 equals 5 or 0 equals 0, the most common one we'd see. If you get a true statement, then what that means is that through all the algebra that we did, all the legal algebra, adding and subtracting, same quantity from both sides, multiplying or dividing by both sides of the equation by the same non-zero or by a non-zero number, all that stuff, you did all the algebra and you always come up with a true statement. That means that it was independent of like it didn't matter what X and Y were, it was always going to be true. So it doesn't matter what X and Y are, you're always going to get a true answer. So that's why it's an infinitely many, because everything will work. So those are the key giveaways. That's the main thing that I want you to take away from this page is that if you get a false statement, it means there's no solution. If you get one X value, it means you're going to get one Y value. You're going to get a unique solution. And then if you get a true statement, it means there's infinitely many. As long as you get those three things, I'm happy. The other stuff, that's for Math 253. That's for linear algebra. Okay? So there are three main ways to solve a system of linear equations. At least in 2 variables, 3 variables is possible to solve. Very, like you have to be able to draw perfect 3D graphs. But anything past that, this method is a moot point. But I do want to talk about it. So method one is graphing. Solving the system 2x plus y equals 7 and x minus 2y equals 6. First thing you're going to do is you're going to want to graph them. And in order to graph them, we need them in slope-intercept form or point-slope form. But point-slope form is kind of hard to make. If it's given in point-slope form, easy to graph. If it's not, trying to create point-slope form is a mess. So it's better to just stick with slope-intercept. But that's not going to be too bad. For the first equation, we'll rewrite it as y equals negative 2x plus 7. And for the second equation, well, first we have to subtract x. So we get negative 2y equals negative x plus 6, at which point we'll divide both sides by negative 2. And remember, the entire right-hand side of the equation needs to get divided by negative 2. So each term on the right, the negative x and the 6 are going to get divided by negative 2, giving us the second equation, y equals 1/2 x minus 3. So these two lines are perpendicular. The fun little tidbit, they are perpendicular because they have the exact same, they have negative reciprocal slopes. Okay. So then, now that we've got them in slope-intercept form, we can plot their y-intercepts, use their slopes to find a secondary point, and then find where they intersect. So I'm going to do this one in red and this one in blue, and we'll see where they go. So 7 is right there, and it's got a slope of negative 2, so down 2 to the right 1 to find another point. And then I've just got to connect those two lines and have a grand old time like that. And that we can label it if we really want to. This is y equals negative 2x plus 7. You can do your best. You get that. Similarly, for the y equals 1/2 x minus 3, that has a y-intercept of negative 3. Plot that point. And it has a slope of 1/2, so that's a rise of 1 over a run of 2. So we'll go up 1 to the right 2 to find the other point at 2 comma negative 2. Right there. And then we will connect those 2 points with a line. I didn't even do it perfectly there. So let's see. There we go. This one isn't perfect either. It should go down a little bit. What's going wrong here? Yeah, it should be. Oh, it should be like that. It should be like that. Okay, so I need to adjust it just a little bit more. And this brings up a very valid point about this method. So y equals 1/2 x minus 3. And so the intersection point is right there at 4 comma negative 1. That's our solution. And then check your work in both answers, right? Check your work in both equations and see if it works. We're good. I guarantee you, if you're bored enough to check it out, you can plug in 4 and negative 1 into each equation, and you'll see that you get the same, you get a true statement. It solves both of the equations. Now, this method is valid. It's important geometrically and to understand what is happening. That's the main reason why I'm going over it, to show us that systems of equations, what it is at the end of the day, is where curves intersect. But it's very, very susceptible to our caveman hands and our inability to draw perfectly straight lines. So unless you have a graphing tool at your disposal, I don't recommend this method. This is mainly a method to visualize. Important, absolutely. Useful, no. It's important to understand what it's doing, but at the end of the day, there are far better ways to solve it. So that's the most we're going to talk about it. Cool? Any questions on that? Key point of this example is that, once again, systems of equations represent lines well, 2x2 systems, 2 equation, 2 unknown, 2 equation, 2 variable. Those represent line in 2D space, and the solutions are the intersection points. So we're going to go over the two main methods. Now, there might be questions on Alex that say, use the substitution method to solve this, or use the elimination or the addition method to solve this. I'm not going to tell anybody if you don't. You can use whichever method you want. Alex won't know, and I won't either. And I don't care too much. That being said, both methods have their merits. So substitution and elimination are both very, very useful ways to solve equations. So it is important to be good at both. Like knowing which one goes better in certain circumstances is definitely a good thing to study. But I want you to be comfortable with both because both are valid. We, of course, will have our own preference. I am usually far more partial to elimination method than substitution, but substitution can sometimes be the only way to solve things. So it is important to get comfortable with both. So solve the systems using the substitution rule. X plus 3y equals 1 and 3x plus 5y equals -5. So what you're going to do with a substitution method is you're going to use one of the equations, it doesn't matter which, to solve for one of the variables in terms of the others. In this case, x in terms of y or y in terms of x, but in later, like in more variables, it'd be like x in terms of y and z, or y in terms of x and z, or z in terms of x and y, and so on and so forth. It doesn't matter which variable you choose as long as you stay consistent. However, I will say it's usually best if you look for a variable that's easy to solve for. Usually its coefficient will either be plus or minus 1, or it will divide every other number in the equation. So for example, I've got an example right here. I wouldn't use the first equation for substitution because if I try and solve for x, I'll have to divide by 3, and none of these numbers are divisible by 3. If I try and solve for y, I'd have to divide by 7, and neither of these numbers is divisible by 7. However, in the second equation, 5 is a really, really nice coefficient on the x because if I bring everything else to the other side to solve for x and I divide by 5, 10 is divisible by 5 and 25 is divisible by 5. So this would be a good candidate for a substitution. Why wouldn't it be a good choice? Because even though like it's nice, the numbers do cancel a little bit, they don't cancel enough. So with this problem, which equation would and I'm going to label this equation 1 and equation 2. This will be useful later on, E1 and E2. Which equation do you think I should use for the substitution? Should I use equation 1 or should I use equation 2? Equation 1, because it's immediate to solve for x. So from here, we get that x is equal to 1 minus 3y. That would be a perfect choice because I didn't need to do any division. I just need to subtract 3y from both sides, and I've already got x in terms of y. And then what you're going to do in the equation you didn't use, like let's underline that or highlight it. In the equation you didn't use, substitute the work you found from step 1 into it. And I'm going to show you why you don't want to plug it into the original equation that you did. You'll see in just a moment. That is to say, what I'm going to do is I'm going to take this. So rewrite the second equation, which was 3x. In step 2, rewrite 3x plus 5y equals -5. And I'm going to take what I just solved for and substitute it in for x. What x is in terms of y. So I'm going to replace x with 1 minus 3y. So this becomes 3 times 1 minus 3y plus 5y is equal to -5. I'm showing this for just a second to show you what's going to happen, and it's going to be confusing. So if you try and plug it into the original of the first equation that you used, you will get a true statement. And that might make you think that there are infinitely many solutions, but it's not the case. You're just doing a circular, you're going in a circle. You use the first equation to write it in terms of x and y, and then you're plugging it back into itself. So it's kind of enveloping itself. It's not useful. The reason why you're plugging into the second equation is because you're trying to solve the system. You need to write one of them in terms of the other to plug it into the other one to see what happens. So, JT, yes.
Bigger system, like 3 equations,
Yes.
does it make a difference what you choose, or?
So yes and no. You don't want to plug it into the original equation that you used, but you could plug it into equation 2 or equation 3.
If you plugged it into one that's missing though, like, and it was just Z,
Mm-hmm.
if it was like 0, Z,
Mm-hmm.
does that mean the X you plug in is just 0?
Yes, and then it would just be 0. So that would be a situation, and that's why when we talk about 3x3 systems here in a little bit, that situation we don't really use substitution. It becomes far too complicated. So a couple things that you might be wondering, why? Why can I do this? And it's because they're equal to each other. I have just imagine on a balance, right? What I've just shown, I've done completely mathematically valid things here. I've only subtracted 3y from both sides. That keeps the equation balanced because I haven't teeter-tottered it at all. So I've got one bag that has x and one bag that has 1 minus 3y, and they're the same amount. And then I've got this equation on a balance, this new equation. So just imagining it just real quick. They are balanced at the moment. Here's -5. Here's 3x plus 5y. I've got that bag of x. And so on the other side of things, I've got this balance of x and 1 minus 3y. They're inside these little baggies. And so basically, what I'm going to do, and sorry people watching the recording, I'm going to pick up this bag, and it's the same weight as x. So I'll just replace it here. I'll take the x bag off and put the 1 minus 3y bag here, and they stay balanced because it's the same weight. Does that make sense? That's why it's mathematically valid that we can do so. You should always be questioning, why can I do that? Because my teacher said so. No. And then what you're going to do is you'll notice now, instead of having two variables, 3x plus 5y, now we have an equation purely in terms of y. So we can solve that equation. So 3 times 1 minus 3y plus 5y equals -5. So distributing in the 3, we get 3 minus 9y plus 5y is equal to -5. Well, that will give me -4y equals -8, which gives me y equals +2. And I'm going to underline it. You don't have to, or you can highlight it. I highly recommend doing so. You'll start to realize in these types of problems that your work can get very, very messy very quickly, especially when you're on a time crunch on an exam and you're not really focusing on being pretty. So it's best to highlight or underline your answers because of that step. So especially help out when we do 3x3 systems. But either way, you're going to solve for the other variable now by plugging in the value you just got into the equation you found in step 1. So we just found out that y equals 2, and we have x equals 1 minus 3y. So we can take this in conjunction and solve for x. X is equal to 1 minus 3 times y, which we found to be 2. And that will give me 1 minus 6, which will be equal to -5. So we have the solution, x comma y is equal to -5 comma 2. And you could just write the coordinate point. You don't have to write the x equals, but I have a reason for that in just a moment. I'll let you finish writing it down, and then we'll talk about it. I did that quickly. A lot going on here, and please ask a question if you're having any curiosity about why this is working or how it works, anything like that. So JT, yes.
Sorry, that's, it'd be the same if you plugged it in, like now that Y value into any of the other equations, right? No
That's
matter
correct.
what's changed.
That's correct. So JT's asking, could I have plugged it in here or here? And the answer is yes. First and foremost, this equation and this equation are the exact same equation. The only difference is that this one, I don't have to do any algebra. I just do a straight plug and chug, as we say. I can plug in like the 1 minus 3 and then plug in the 2 and I'm all done. Whereas if I do it here, then I do have to just subtract the 3y over, the 3 times 2 over. And here I need to do a little more algebra, but it should solve any of the equations. So I can use any of them to solve for it. What was I going to say? Now, a couple things. So I've underlined both of my solutions because the answer isn't x equals -5, y equals 2. The answer is an ordered pair. The solution to a system is an ordered, triple ordered, tuple ordered, quadruple, whatever it may be. But it's always going to be a point in 2 space, 3 space, 4 space, whatever it may be. So that's why I always write the x comma y, because sometimes, like in this case, I solved for y first. And so my lizard brain starts to go, oh, I found 2. 2 is the first one, so I write 2 comma -5. But the answer is -5 comma 2 because the x coordinate comes first. Does that make sense?
Yes.
So don't be a lizard brain like me. Underline your values so that you know which one goes where. And then if time permits, verify your answer by checking it's the solution to both equations, blah, blah, blah. You know the deal. The great thing about it is that you can check your work, but that's if you're unconfident with your algebra. If you have time on the final exam to check it out and make sure that it all works out, do so. But if you don't have time, don't worry about it. But we're good. We can do it in our heads. We can do it on our calculators, however you want to do it. The good news is that with systems of equations, you usually have all the variables on the left and a number on the right. So as long as you plug in the numbers into your calculator, right, just do 3 times -5 plus 5 times 2 and see what number you get on the calculator. It should show up as -5 and you'll be good. So you don't need to like check both sides because one side is already just a number. But either way, let's go ahead and take a break. Let's come back at 10:10 and then we'll do some examples. 10:10. I'm going to pass back some exams and stuff. And so we'll see you in 7 minutes. All right. So we'll do a couple examples here. We'll do A and B. Like I want to make sure we get through everything we can. And we do need to go over applications, quote unquote. So we'll do that in just a moment. So 2x plus 5y equals -14, and then 2x plus y equals 2. This is a prime candidate for substitution because the second equation would be a perfect candidate for substitution because the y is already got a coefficient of 1, so I don't need to do really much algebra at all for substitution. So this is the same thing as saying y equals -2x plus 2. And I will take this and I'll substitute -2x plus 2 in for y. So we get 2x plus 5y, but y is equal to -2x plus 2 equals -14. And we'll solve that. Yes, Jake.
All right, you just solved for y. That was just because y by itself.
There's nothing wrong with solving for x there. You could do it. You could solve for x. So you could do this instead. You could do, so 2x is equal to -y plus 2, and then divide both sides by 2, and get that x is equal to -1/2 y plus 1. And you could substitute that in instead. And you'll get the same answer at the end of the day. And it actually won't be that big of a problem, luckily, because it like the 1/2 and the 2 are going to cancel out in the first equation. So that will work out. Sometimes it does, sometimes it doesn't. But If you're bored this weekend, definitely try it out. Because it's not like there's anything going on next week. So you guys probably have plenty of time this weekend to just fool around and do nothing, right? Is anything happening next week? By the way, as a reminder, our exam is on Tuesday. I tried to make sure, like, I tried to, our final exam is on Tuesday. I was hoping to, like, a lot of teachers love to schedule things on Monday, so I was hoping to kind of counterbalance that. I'm willing to work with you guys. If you guys have more than one exam on Tuesday, contact me, and I'm happy to kind of work with your schedule. Maybe you can push it a day or a day later so that you don't have to have too many exams in the same day. Just let me know. So anyway, solving this one, not too terrible. It's a linear equation. So this is 2x minus 10x plus 10 equals negative 14. That's negative 8x is equal to negative 24. So I did two steps at once there. I subtracted the 10 from both sides, and then I simplified the 2x minus 8x. And then I'll divide both sides by negative 8 and get that x is equal to positive 3. And then I'm going to take this information with this information to find that y is equal to negative 2 times x, which is 3, plus 2. That's negative 6 plus 2. That's negative 4. So that gives us the solution 3 comma negative 4. That's our x comma y. If you just want to write the coordinate point and you don't want to write x, y equals, that's fine. It's just as a reminder that it's an x, then a y. Any questions on that? Assume. We'll do the next one, and then I'll save the other one for later if we have time. But we'll get to it in just a moment. So this one, part B, nice and neat for us. One of the variables is already solved in terms of the other. So it's going to be a very quick problem, at least so we think. Yes, it has fractions. Yes, those aren't the best things ever, but it's not too terrible. All we need to do now is plug this in for y. So when do we end up with? Oops, wrong color or wrong type of pen. So 2x plus 3 times y, which is going to be negative 2/3 x plus 5 equals 11. I'm replacing y with what it is in terms of x. And we're going to luck out here with the fact that the 3 is going to go into the 3, the negative 2/3 and cancel it. Whew. Lucked out. And so we end up with now 2x. When you distribute the 3 and you get minus 2x plus 15 is equal to 11. But then the 2x and the minus 2x cancel out and we get 15 equals 11. That's a false statement, which implies that there is no solution. If we end up getting 15 equals 15, then it would be infinitely many. But we ended up with 15 equals 11, which is not a true statement. So there is no solution. Yes, JD.
Does that mean if it was on a graph, they'd be parallel?
Yes. On a graph, these two lines would be parallel to each other because they'll never intersect. And the only way you get a solution is if the two curves intersect. Great point. And you'd actually see that if you solve for this, just as an aside. If we write this equation, the second equation in slope-intercept form, you'll see we get 3y equals negative 2x plus 11. Divide both sides by 3, you get y equals negative 2/3 x plus 11/3. So they are very close to each other, but not. They have the same slopes, so they're parallel, but they have different y-intercepts, so they aren't parallel. But anyways. Yes, JT, yeah, did you follow?
I was gonna say, if you saw that, like, based on slope, they would be parallel,
Mm-hmm.
could you just go straight to no solution?
Absolutely. If you notice that they were parallel, ideally try and mention it. So like, remember the whole goal is that you're trying to explain this to it, like your work should show that you're explaining it to another student. So you probably want to write parallel and then write no solution, and that would be enough. But yeah. So in the interest of time, I'm going to tell you what the answer to this one is. This one is infinitely many. And the solution set will be of the form x comma 1/4 x plus 3/2. That'll be the solution to this problem if you want to check it at a later date or if we have time at the end. But I want to make sure we have both methods under our belt so we can use both of them in any situation. So any questions on the substitution method? Nothing too crazy, I hope. We're going to see contrived examples in a moment, but that isn't to say that there aren't other cases where these things can be applied to real life. So we move on to the elimination, or sometimes called the addition method, and how it's going to work. So first and foremost, in order to get this to be really, really useful, you're going to make sure that all equations are of the form ax plus by equals c in standard form or general form for a line. So the second equation is already in that format, but the first equation is not. So we'll add 3y to both sides to get this to be in the right format, which would therefore be x plus 4y is equal to 2, and 2x plus 5y equals -2. That's our new and improved system. We haven't done anything illegal. We haven't done anything crazy. We just added 3y to both sides on the first equation, which we can do. That's mathematically valid. That doesn't change the solution set. Then what you're going to do is once you've done that, you're going to, as needed, multiply one or both equations by constants so that the coefficients on one of the variables are opposites. They're the same number, but opposite signs. So you want to get like 3 and -3y, or -2x and 2x, or 2.5y and -2.5y, whatever the case may be. So looking at this situation, I'm going to rewrite them, but without the curly brace. So I got x plus 4y equals 2, and then 2x plus 5y equals -2. So I could either eliminate x or I could eliminate y, but there's a better choice. There's a best choice. What do you think I should eliminate? Should I eliminate x or should I eliminate y? That's correct. I should eliminate x because in one of the equations, the leading coefficient is 1, so I don't need to multiply the second equation by anything. I can just multiply the top equation by -2, and I'll be good. Because I want the x terms to have same number, opposite sides. Opposite signs, not sides. I could try and eliminate y, and that would be fine. What I'd have to do is I'd have to multiply the top equation by 5 or -5, depending on what I want to do, and then the second equation by -4. And if I do that, then the y values, the y variables will have the same coefficient but opposite signs, and then I will take care of it that way. So that's what we can do, but there's usually a better choice. And so in this case, the answer is to multiply by -2. As a little pro tip, I highly recommend having an extra pen with you, like a colored pen, so that you know that this needs to be applied to the entire equation. That's why I've put it in pink on both sides to remind myself that everything is going to get multiplied by -2. Plenty of students have done this as well. That's okay too. You can multiply both sides, even though that kind of looks like you're raising it to the second power, the -2. You can do that as well. JT, yes.
So it's -2 because, you know, -2 is the answer on the bottom one, or is it because it's the opposite of what's in front of the x in the bottom one?
It's because it's opposite. Yeah, same number, opposite signs. And you'll see why once we get to the next step, why we're doing this.
Okay.
So if I do multiply that entire equation by -2, my new system is going to be -2x minus 8y equals -4. The most common mistake I see students make is they correctly multiply -2 into the left-hand side of the equation, but they forget to do it to the number on the right. So please don't make that mistake. That's why I put it in colored parentheses to say everything is getting multiplied by this. And then the second equation, we didn't do anything to it, so it stays as 2x plus 5y equals -2. So the good news is we haven't done anything illegal, so the solution set is the same. We just negatively doubled the first equation on both sides. So that doesn't change anything about the equation. I mean, it changes the numbers, but it doesn't change the solution. And so this is why it's sometimes called the addition method, because we're going to add these two equations together to eliminate one of the variables. So we've got -2x minus 8y equals -4, and then 2x plus 5y equals -2. And we're going to add these two equations together. While you're writing that down, I'm going to mention something. So when we add these things together, don't worry about the things that I've drawn below. I'm gonna explain them in just a second. I'm gonna explain why we can do what we just did. So the -2x's will cancel. That's a question this moment. And then we've got -3y because it's going to be -8y plus 5y. That's -3y. And then -4 plus -2, that's -6. And so we have eliminated x. That's why it's usually called the elimination method. I have eliminated x from the equation. And now it's just a simple division. Just divide both sides by -3. And we get that y is equal to -6 divided by -3, which is +2. And I'm going to underline it to remind myself that that's the y variable. Question is, why can I do that? Why can I add the two equations together? And it's because if you think about them like a balance, right? I'm going to kind of make these ones smaller. So they're easier to grab. So I have both of the equations here. And since they're equations, they're balanced on both sides. And what I'm going to do is I'm going to add these two equations together. I'm going to take this and add this one as well. But if I add both of those to one side of the equation, then I can also, since both bags are the same weight in the blue and the red, I can add these two things together. That's why I'm allowed to do this, because they're both equal to each other. Does that make sense? Is that visually understanding why this is possible, why I can add the equations together? I can add the left-hand sides together because they're equal to the right-hand sides added together. That's why this works. But if you want to see a different explanation, I can try and think of one. Anyways, so now that we solve for y, we can substitute that value in step 3 into either one of the original equations to solve for the remaining variable. Usually you want to use the one that's easier. So I'm fairly confident that I wrote these things correctly. So I'm going to use this version of it, but you could use either one of these. It would probably be a safer bet to use these, since that's the first time it was presented without any human error possibly getting introduced. And so since we're solving for x, I think the first equation would be perfect because I don't need to do any division. But you could use the second equation. It wouldn't be wrong to do so. So what I'm going to do is I'm going to take that y equals 2, and I'm going to take the first equation, which was x minus 4 or x plus 4y equals 2. And then take this information to solve for x. I get x plus 4y, but y is equal to 2 equals 2. That gives me x plus 8 is equal to 2, which gives me x is equal to -6. And so my answer is the point x comma y. So it's going to be -6 comma 2. And then, of course, we can always just check our work at the end to see if it works. And it will. If you plug in -6 comma 2 into either one of the first equations, it will solve it. We're going to assume that we did it. For the same reasons above, you can just plug in those values in the left-hand side of the equation and then press enter. And as long as you get the number side on the right, you're good. Because that means you got a true statement. Any questions on that? JT, I think you had a question, but I forgot to.
Oh, yeah, I was just curious. Is there like ever a time where we'd have to use a specific one, or can we like always choose? Like if you're more comfortable with the second option?
Yeah, you can really interchange it.
Okay.
It's very, very moldable to your situation. As you do more and more of these things become much like you start to realize the intuitions as to like when you want to use one over the other and when it will be better to solve for x in terms of y first or eliminate x first, or whatever it may be. Any other questions? All right. So this first one here, there's no clear winner as to which one. I mean, there is a better choice, but not by much. You think it'd be better to eliminate x or to eliminate y? I would argue that they're just about the same. Because 4 doesn't go into 7, 3 doesn't go into 2, so we're going to have to try and find something that they both like we're going to have to multiply both equations by something to get a common coefficient. I would argue that y would be the better equation, the better variable to eliminate because they already have opposite signs. So I don't need to multiply by negative numbers at all. But either way, this is not a good candidate for substitution either because no matter which variable you try and solve for, you're always going to end up with a bunch of fractions. So it's best to use elimination here, in my opinion. So I'm going to try and eliminate y, which means I'm going to take the first equation and multiply it by 2. And take the second equation and I'm going to multiply it by 3. So that gives me 8x minus 6y is equal to 18. And 21x plus 6y is equal to -18. I chose 2 and 3. Question, just a moment. I chose 2 and 3 because I wanted them to have the same y value. The way you're going to do it basically is you're looking for the least common multiple, the smallest number that they both go into. That being said, you could totally just always multiply it by the two numbers involved. Like multiply the first equation by the second one's number, the second equation by the first one's number, and call it good. It'll always work out that way. It's just you'll end up with large numbers sometimes, and that can be a little uncomfortable at time periods. JT, you got a question?
I guess now that's it. But I was just curious, how come the 2 doesn't become a negative when you multiply it? It's just you need the y to cancel out.
Yes, because I need the y's to cancel out. So that's why I didn't multiply by -3 or anything like that.
So you
Because
can choose to make it a negative number.
yeah, you can. You can multiply any equation by any number. So if I wanted to eliminate x, by the way, if I wanted to do that, just so you can see it, 4x minus 3y equals 9, and then 7x plus 22y equals -6. What I would have to do in this case, the smallest number that 4 and 7 both go into is 4 times 7, which is 28. So I'd multiply the first equation by 7 or -7, depending on what I wanted to do. And then I'd multiply this one by -4 to get that 28. And that will end up working out just as well. It just ends up being a couple like slightly larger numbers. But it still works out. Anyways, now what I'm going to do is I'm going to add these two equations together. And the 6y's will cancel because it'll be negative 6y plus positive 6y. They cancel. And then 21x plus 8x, or 8x plus 21x is 29x. And then 18 plus negative 18, that's 0, which means that x has to equal 0. And then I can use either equation, first or the second. I would argue that the second equation would be easier because I don't have to deal with division by a negative number. But honestly, at the end of the day, it doesn't really matter. As long as you're comfortable with, like, you do your algebra correctly, you're fine. So I'm going to take the 7x plus 2y equals negative 6. And in conjunction with the fact that we know that x is equal to 0, then I plug in 7 times 0 plus 2y is equal to negative 6. That gives me 2y equals negative 6, which gives me y equals negative 3. So the answer is x comma y equals 0 comma negative 3. Solution is the coordinate point 0 comma negative 3. The next one, unless there's any questions on the previous one. So this is the elimination method in action. Get one of the variables to have the exact same numbers with opposite signs, add them together to cancel it, solve for the remaining variable. Yes.
If it would have made this y equals mx plus b, then would you just see that they all have a -3 there?
Probably, yes. You could do that, yeah. And so they have the exact same y-intercept. That actually, that's a very good way to see it as well. Since they're like, if you write them both as lines, you'll see that they have the exact same y-intercept. So that is a y-intercept that they both share, i.e. an intersection point. That's a good point. Quite literally, it's a good point. That wasn't a good joke. Don't laugh at that. That was a low-hanging fruit right there. Okay, we're gonna do B, and then I'm gonna give you the hint on how to do so. Yeah, I'm gonna give you the hint on how to do C first, and then I'll give you the answer. This next one, 3x plus 2y equals 6, and negative 6x minus 4y is equal to negative 12. I think both cases would be okay for substitution or elimination. Not pretty, but not too terrible. But I think elimination still takes the cake. And I could eliminate either variable because 3 goes into 6 and it goes and 2y goes into 4y. So either one would be a good option. I'm going to multiply by 2 to get rid of the x's because that will get me to a positive 6x and a negative 6x. We're going to see something interesting. So you get 6x plus 4y equals positive 12, and then we've got negative 6x minus 4y equals negative 12. Interesting. Interesting. So when we add them together, in fact, everything cancels, and we get 0 equals 0. We get a true statement. And that means that there's infinitely many solutions. And then to find out the equation, like to find out the formal answer, I would be accepting of writing infinitely many solutions. If you write that on your exam, if this type of problem shows up, I will give you full credit. I will 100% give you full credit. No need to worry about it. But if you want to write it specifically as a mathy answer, you'll take either one of the equations and write it in y equals mx plus b form. You can use either equation because they're the exact same equation. That's the reason why we have infinitely many solutions. They both are the same equation. So it doesn't matter which one you do. I'm going to choose the simpler one, the 3x plus 2y equals 6. Solve for 2y, or solve for y. So we'll use negative 3x plus 6. We'll divide both sides by 2 and get that y equals negative 3 halves x plus 3. So that's the equation of that line. So every point on that line, which is going to be a point x comma -3/2 x plus 3. Every point on that line can be found by that coordinate point. You plug in x equals 1, you'll find the corresponding y value by plugging it into that equation, the -3/2 x plus 3. But honestly, I prefer if you just write this. We're not in linear algebra yet, so we don't need to worry about those weird those weird answers. We just need to know that there's infinitely many. That's all I care about. As soon as you get a true statement, 0 equals 0, 5 equals 5, that means there's infinitely many solutions. Any questions on that? The last one here is to remind us that we don't need to be scared of fractions. Fractions are people just like you and me, so we just need to work with them ourselves. Usually the best way to work with fractions is to get rid of them, just kind of push them into the background. And so, pro tip, get rid of the fractions first. By multiplying each by its LCD. I should probably put that above. Sorry if you haven't. So multiply by the LCDs to get this thing to make it look a little bit prettier, because in its current format, it looks a little bit nasty with all those fractions. And I prefer not to use the substitution method or the elimination method here. It would be awful. Trying to get the x's to have the exact same coefficient would be a very, very nasty thing to work with. So instead, what we're going to do, multiply the first equation by 10, because that's the least common denominator of 2 and 5, and multiply the second equation by 3, because there's only one fraction, that 5/3. Doing so will get me 10 times 1/2, that's 5, so 5x. 3/5 times 10 is going to be -6. Yeah, so minus 6y, excuse me, equals +8. And then the second equation, I'll get 5x minus 6y equals 15. And I think you might see it already what the answer is going to be. And if you don't, that's okay. We can still solve it just like normal to figure out what the answer is. But you might notice that these are the exact same equation, which means it's going to be the left-hand side is the same, same parts, and the right-hand side is different numbers. So there's not going to be any solution. But we can still do it by elimination. We'll multiply this one by -1 to get the x's to be opposite signed. And we get 5x minus 6y equals 8. And then -5x plus 6y equals -15. At which point we'll add them together. And you end up with 0 equals -7, which is a false statement. So there's no solution. But so yeah, if you see fractions, immediately try and get rid of them. You can multiply an equation by any non-zero number, so get rid of the fractions. Very, very useful. All right. Any questions? Yes, JT.
The, um, oh, actually, never mind.
Good?
Yeah.
All right. Good. So everyone's favorite subject next, everyone's favorite thing, applications. I know we're all super giddy about this. This is the best part of this section. And my helpful starting tips though, because remember, there's no way to solve an application problem that works for every application problem. But there are things that we do know that are helpful. So first and foremost, whenever I do these ones, I'm always asking myself, what am I trying to find? Usually it's usually mentioned in last sentence. Usually the last sentence of any application problem is telling you what it wants to find. Then, using your answer to the question you pose to yourself, what am I trying to find? Define your variables. Unless the variables are defined, unless it says where x is blank and y is blank, you need to define them. Otherwise, there's no clear indication of what x and y are. Then, the key thing is to convert the statements into mathematical equations. So like is equal to equals. Product means multiplication. Difference means subtraction. Sum means addition, and so on and so forth. And then please define your variables. Please, please, please. You really need to define them. Otherwise, you're going to be in a world of hurt. So, for example, a family has 2 cars. The first car has a fuel efficiency of 30 miles per gallon, and the second has a fuel efficiency of 25 miles per gallon. Last week, the 2 cars drove for a combined total of 1,700 miles, which I just realized is way too obscenely large for a week. They both went on road trips to Disneyland and back, apparently, for a total gas consumption of 60 gallons. How many gallons were consumed by each car that week? So we've read the question, we've tried to interpret it, and it says how many gallons of gas. This first, the last sentence, that tells us what we're trying to find. So we're trying to find the gallons of each car, the gallons of gasoline used in each car. So we're going to let X equal the gallons of the 25 mile per gallon car, and Y equal the gallons of the 30. The first one should be 30. And the 25 mile per gallon car. This doesn't need to be super explicit here. Doesn't need to be super explicit on this application. You could just say let X equal gallons of first car and Y equal gallons of second car. That would be sufficient. And if you're really on a time pinch, I'm sure you could write X equal gallon and Y equals gallon, and that would be okay. So now that we've defined our variables, oh, did you have a question? Okay. Now that we've defined our variables, we can start taking all the information given to figure out equations. So there's usually a nice, neat equation to come out, and then there's one that requires a little more work. Can we think of one of the equations? Knowing that X is gallons of first car and Y is gallons of the second car. There's information here that we can use. Grace, did you have were you going to say or okay? All right. That statement for a total gas consumption of 60 gallons. How could I use that into an equation? How could I convert that information into an equation, knowing what X and Y are? Yes, it is 60 gallons. The number, you could restate this statement and say the number of gallons of gas added together is equal to 60 gallons. That is to say, from this information, I can say that X plus Y is equal to 60. I know that if I take the gallons that were used by the first car plus the gallons of the second car, it should add up to a total of 60 gallons. Now, the second equation is a little more difficult to find out unless we start to think about it mathematically, like with unit conversions involved. I'm going to take this information. Let's do red. Using this information, I can figure out the next part. We know that the first one has a fuel efficiency of 30 miles per gallon. So if I took its fuel efficiency and multiplied it by its number of gallons, I would get the total amount traveled by the first car. Similarly for the second car, right? If the first car drove 10 miles, or sorry, if the first car used 10 gallons of gasoline, it would have traveled 300 miles. And that would mean the other one traveled 50. And then I could multiply it by its miles per gallon, and that would give me the total miles traveled by the second car. That is to say, if I take 30x, 30x plus 25y, I will get 1700. This gives me miles. 30 miles to the gallon times the number of gallons. The gallons cancel, I get just miles. 25 miles to the gallon times the number of gallons of Y gets me the number of miles traveled by the second car. Any questions on that? This is not something that is easy, by the way. Taking English and converting it into mathematics can take a lot of time. It can take a lot of experimentation. You'll never know until you put your pen on the paper, though. And honestly, if this type of a problem shows up on the exam, I'm not sure if it will, but if you define your variables, I will give you at least 2 points of partial credit, because that is such an important step. If you assign your variables, it's much easier to come up with the equations. Any questions on how I found those equations? From here, it will be either elimination or substitution. I would think substitution would be easier, but elimination could work out. So I'm going to solve for x in terms of y, but you could do y in terms of x, whatever you want to do. So I'm going to make x equal to 60 minus y, and I'll substitute this in for x and get 30 times 60 minus y is equal to plus 25y is equal to 1700. And we're out of time. We'll call it good for now. We'll finish it up. The answer should be x equals 40 and y equals 20, but we'll finish this up next time. Okay, guys? Should get x equals 40 and y equals 20 if you want to do this later today. If you have any questions, feel free to ask. Otherwise, please remember your exam 3 redo is due on Wednesday, and then I'll post the solutions later on that day, okay? I'll be posting all the blank exams and the exam solutions very, very soon, so you can use them to help study for the final exam. If you have any questions, again, feel free to email me. Otherwise, write your congressperson, yada, yada, yada.